Hi everyone, welcome back to chemistry. In this video, we're going to start our study guide number 6, which is all about quantitative aspects of solutions. So how do we quantify different things in solutions? So determining things like the concentration of a solution, which is, how much solute is dissolved in our solvent. How do we dilute some kind of solution that's a certain concentration to a different concentration? How do we figure out the pH or, acidity or basicity of a solution, stuff like that. So we can quantify all of those characteristics using what we know about solutions. So first, we want to learn about solutions a little bit more because we've talked about them a little bit. We've actually already gone over 9.3, which was about solubility. But now I want to get more in depth. So this video will be about 9.1 solutions, so introducing what they are. So what are solutions? So solutions are homogeneous mixtures of two or more substances. And we said before that, remember, our solute is the thing that's being dissolved in our solvent, which is the thing that we're dissolving something into. So in this case, our solute is salt. And we're dissolving that salt into our solvent, which is water. Okay, you could think of it like the solute is the thing we have less of, and the solvent is the thing we have more of, if that helps. So what are solutes? So remember, solutes are the things we're dissolving. So solutes can actually be a liquid, gas, or solid. So a lot of times when we think about solutes, we think about solids specifically. So like salt or sugar, we think about them in the solid form and you're dissolving that into a liquid like water. But actually solutes can be liquids or gases as well. A common gaseous solute that you are familiar with is carbonated beverages. We dissolve CO2 in those carbonated beverages, and that's what makes them all fizzy. Liquids could be, I don't know, like liquid sugar that we dissolve in iced coffee to make it easier to dissolve, and stuff like that. Solutes are also spread evenly throughout the solution. So that's what it means to actually dissolve something, is to have it spread evenly throughout the solution. If you see a solute in solution, that actually means that it didn't dissolve all the way, right? And we saw that with precipitates that we formed in lab during our precipitation reactions lab. You saw some things dissolved really well. You couldn't see them in the solution. You just knew that they dissolved because you put the solid in there and then suddenly it was a liquid. But some of them actually precipitated or formed solids. So things like that. If you notice a solid in there, that means it wasn't soluble. The compound that you made or originally started with. All right, so let's see. Let's keep going on here. So a lot of times we talk about water as a solvent because water is just one of the most common solvents that we have in nature. It's very abundant, though it is non-renewable, of course, right? But there's a lot of it around and we're very familiar with it, so it's a common solvent. And if you remember, we did talk about something called polar molecules and polar bonds, or bond polarity. So we talked more about bond polarity than molecule polarity, but they are different. So I do want to get into it just a little bit more. And to do that, I want to go over here for a second and look a little bit closer at a water molecule. So our H2O, or our water molecule, it's a molecule, right? So what does that mean? Let's just kind of review a little bit. Remember, molecules are covalently bonded atoms. So we've got, or I guess atoms that are covalently bonded make up a molecule. So we don't use the term molecule for ionic compounds. We only use them for covalent compounds. So if you hear the term molecule, you know it's covalent. And remember, what does covalent mean? That means sharing. So covalent, sharing valence electrons, like cohabitating is sharing a home. So we have a covalently bonded molecule here. We have atoms that are covalently bonded. They're sharing those electrons. But remember, we said that some atoms actually like to hold electrons closer to themselves than others. They really, really, really want electrons. So they kind of like, even if they're sharing with another atom, they'll kind of hog all the electrons to themselves. And that's called electronegativity. So the more electronegative an atom is, the more it likes to hog those electrons, the more it wants those electrons, and it will pull them closer to itself. And remember, we said that within a bond, we can determine if that bond is polar or not by comparing electronegativity values and determining the difference between electronegativity values for each atom within that bond. So we said, okay, well, we can look at an electronegativity chart and we can determine, okay, what are the electronegativity values for something like oxygen versus something like hydrogen? Okay, and then we can say, all right, well then, is this bond polar or non-polar? And we had this whole kind of chart that said, you know, difference of electronegativity of such and such value makes the bond polar, a difference of this makes it non-polar, stuff like that. But just in more general terms, if you're looking at the periodic table, we said that electronegativity increases as we go right and up on the periodic table, or kind of like diagonally like that. So oxygen being at the top right of the periodic table, it's really electronegative. It really, really wants electrons. So it's actually going to kind of steal those electrons kind of closer to itself. Still sharing with hydrogen, but it wants to hold them closer. It's like, I really, really like these electrons. So what ends up happening is, because it's kind of hogging all the electrons this way towards oxygen, and electrons are negatively charged, that oxygen ends up having a partial negative. Okay, is this ringing a bell? On the other hand, hydrogen, because it's less electronegative negative than oxygen, it's on the left side of the periodic table, its electronegativity value is less than oxygen, it's going to say, okay, oxygen, you can have those electrons. You can hang on to them closer if you want. I don't really care. I'm happy just being partially positive. So within this bond, we've got oxygen with a partial negative charge and hydrogen with a partial positive charge. They haven't gained or lost electrons, but they're just kind of holding them. They're sharing them unequally. And let's actually write this down. Sharing E unequally, just as a review. All right, and this is actually happening on this bond as well. So this bond right here, okay, we've got that oxygen still with that partial negative and that hydrogen with that partial positive. So I'm actually going to draw this here. Yeah, let's draw it there. So now when we're looking at this molecule as a whole, well, actually rewind for just a second. So remember, we also said that you can now draw dipole arrows. And dipole arrows show you, they basically show you which side of the bond is partial positive and which is negative. And you'll draw them with the positive side. This is the positive side with that little plus, and then the other side is going towards the negative side. Okay, so those are your dipole. That's a dipole arrow. Dipole arrow. So we said, okay, we can draw those like this, right? And I'm just drawing them with the positive side near hydrogen and pointing towards the negative side. I just remember it with this little plus right there. All right, so those are dipole arrows on our bonds. We can also draw something called a net dipole arrow, and we'll do that maybe in purple. Net dipole arrow. And that is going to be showing what the entire molecule, where those charges are in the entire molecule, so those partial charges. So if we're looking at this, notice that if we have a bunch of those negative kind of electrons kind of hanging out on this side of the molecule, we've got all those negative charges on that side. So what ends up happening is this side of the molecule is very it's very dense with electrons. We've got a lot of electrons kind of hanging out in that region, and then a lot less on the hydrogen side. Okay. So we can draw a net dipole to show that phenomena, to show that, hey, there's more negative charge on this side of the molecule. So, and the way we do that is we kind of average those two green dipole arrows to draw a net or a full overall dipole. So again, we've got, if we're looking at this molecule, we've got kind of like a positive side down here going towards a negative side at the top. Okay, so that would be your net dipole for that molecule. All right, and what is this saying? It's saying that most of our positive charges on this end, on this side, and most of our negative charges on the other side, on the top, the way I've drawn it here. All right, I hope that makes sense. So that's dipole arrows, net dipoles, and bond polarity versus molecular polarity. So the green arrows are showing that bond polarity, right? And that purple arrow is showing that molecule polarity. Okay, so why does this matter? Why does it matter that water is a polar molecule? Well, what's interesting is that because water is a polar molecule, it's actually attracted in some areas to other areas of another water molecule. So looking down here, let's zoom in here. Notice that we've got, you know, these are our water molecules. This is a water molecule, so is this, and so is this. They've just drawn them more realistically than my little Lewis structure up here. But it's the same idea. So you've got that partial negative charge on that oxygen and that partial positive charge on the hydrogens. And what ends up happening is, remember, we've got all of these water molecules in, you know, our beaker or whatever, and they can react with each other, or they can interact with each other, and they do. So because we've got those partial negative charges on our oxygens and those partial positive charges on our hydrogens, if we have one partial negative on one water molecule, it's going to be attracted to the partial positive on another water molecule in a different area, and they'll kind of orient themselves because that difference in charge is creating kind of an attractive force. All right, so why am I talking about polarity? Well, it turns out that solutions will form when the solute and solvent have similar polarities. So when they have similar polarities. So what does that mean? So let's look at this table here. And I'm looking over on this side right now. So on this table, it says these are possible combinations of solutes and solvents. So solutions will form, they will form when your solute is polar and you're dissolving that polar solute in a polar solvent. Okay, when your solute and your solvent are both polar. Solutions will also form when your solute and solvent are nonpolar. So my favorite example of this concept is to think about, okay, if we have water, which is, we just talked about how water is polar. It's a polar molecule, so it's a polar solvent, right? It's one of our favorite solvents. So if water is a polar solvent, and we try to dissolve oil in it, what do we see happen? Yeah, the oil doesn't dissolve. Why do you think that oil doesn't dissolve? Do you think it's polar or nonpolar? Yeah, it's nonpolar. So solutions will only form when both the solute and solvent have similar polarities. They're either both polar or both nonpolar. Solutions will not form when the solute is polar and the solvent is nonpolar, or the solute is nonpolar and the solvent is polar. But why? Why is that? I'm going to skip these, and I want to talk about ionic solutes. So we've talked about kind of, polar molecules, and I want to start thinking about polarity kind of as a spectrum again. So let's go over here for just a second. And I want to remind you of that, do you remember in that bond polarity quiz question, there was this chart, and it kind of showed, and this is a simplified version, but it showed polarity, increasing polarity going from left to right. And we said, okay, if we're on this side of the arrow, we're not polar at all. And that would be, an example of that would be a non-polar covalent molecule. And then we said at the other end of the spectrum, we could have ionic compounds, right? Those are things that they don't have a partial positive, they don't have a partial negative, they have a full positive and a full negative charge, right? Nonpolar covalent, those are sharing electrons evenly, right? And then we said there's something in the middle, and that's polar. Let me give myself a little more room here. And that's polar covalent molecules. And polar covalent molecules are still sharing electrons, right? They're covalent, but they're sharing them unevenly. So I just wanted to remind you of this because I want you to start thinking about polarity as a spectrum. So when I say polar or nonpolar, yes, there's polar molecules and nonpolar molecules, but when I'm talking about substances, ionic compounds are kind of like the most polar you can get, right? Because they've gained or lost electrons to form full positive and full negative charges, okay? So just kind of a sidebar there. In order to talk about ionic solutes, so think about NaCl, table salt. We know from just our everyday life that it's really easy to make saltwater solution. And the reason for that is actually it's chemistry, right? So when we have our NaCl solid, right, and we dissolve it in water, what ends up happening is we actually separate those Na plus or sodium ions, cations, and chloride ions, anions. We separate those ions, and that's what is actually causing those NaCl crystals to dissolve in water. So let's take a look at that a little bit closer. So remember we said that, I made a little mark there, that we have here's our water molecules, right? And we're putting this NaCl, this sodium chloride crystal into, it's a solid, right? Into our water, and it's dissolving. Why is it dissolving? So what ends up happening is, remember, we've got that partial negative charge on our oxygens and the partial positive charges on our hydrogens. So what ends up happening is our negative charges on our chloride ions, right here, though that negative charge is attracted to the partial positive on our hydrogens. Okay, and what ends up happening is that water, as it orients itself around these crystals, those chloride ions are actually separated because those water molecules are going to orient themselves like this around that chloride ion. Chloride ion. Ooh, can't talk today. And they're going to pull it apart. Likewise, with the sodium ions, we're going to have that partial negative charge on our oxygens being attracted to that partial positive charge, that full positive charge on sodium. And the same idea, they're going to surround that sodium ion. Yeah, and that's what's causing that NaCl crystal, that solid, to dissolve in water. It's breaking up into its individual ions. Pretty cool stuff. All right. So, when solid lithium chloride is added to water, why do you think it dissolves? And we'll do this learning check together. So why do you think it dissolves? So for the first part, it says the lithium ions are attracted to the what? Oxygen atom or hydrogen atom in water? Lithium ions. If you said oxygen atom, you would be correct. And the reason for that is, right, your lithium has a positive charge on it. It's a lithium ion, it's cation. It's lost an electron to become positive. And that positive charge is now attracted to that partial negative charge on that oxygen atom. And then for part B, we've got our chloride ions, right, which have formed a -1 charge. Why? Because it's if lithium gave its electron to chlorine. And now chlorine has a -1 charge. So if chloride ions are attracted to what? The oxygen atom or the hydrogen atom in water? Yeah, the hydrogen atom, right? Because now that negative is attracted to that positive. So opposites attract. All right. So let's check out this learning check. So which of the following solutes will dissolve in water and why? Pause the video, try it out. All right, so a couple different parts to this. So the first thing I think as I'm looking at this question is I'm like, okay, what would cause something to dissolve in water? Well, water, right? Water is a polar solvent. We said it's a polar molecule. So it's a polar solvent. So what dissolves in polar solvents? Polar solutes or non-polar solutes? Yeah, polar solutes. So we're looking for any of these need to be polar solutes. So A, Na2SO4. B, gasoline, which we're told is non-polar. I2, which is what? Yeah, iodine, right? I2 is iodine is one of our diatomic molecules. Okay, molecules. And then HCl. What's HCl? Yeah, hydrochloric acid. All right, so which one of these can we knock off right away? Yeah, let's get rid of that one because we know it's non-polar, okay? So it's not going to be that. So let's say no like dissolves like. All right, what about the top one, Na2SO4? What is that? Yeah, sodium sulfate. Good. What's sulfate? Yeah, it's a polyatomic ion. With what charge? 2-. Yeah. All right, so if sulfate has a 2- charge and we have 2 NAs, it must have a 1+ charge. Another way you could do that is you could look at the periodic table and you'd say, okay, sodium's in group 1. It loses 1 electron and it has a +1 charge or 1+ charge. All right, so is this compound ionic, polar covalent, or non-polar covalent? It's ionic, right? It's ionic. So do ionic compounds dissolve in polar solvents? Yeah, they do. Yeah, remember, ionic compounds are kind of like the most polar that you can get. Okay? It's not in the name, but they're ions, right? They have full charges. So they like to dissolve in water. So let's say yes, because ionic. All right. What about, and I'll put a little check mark. What about iodine? What do you think for that? Yeah, that one does not dissolve. And why doesn't it dissolve? What is iodine? Is it ionic? Covalent? Yeah, it's covalent, right? How did I know it was covalent? 2 nonmetals. Nonmetal plus nonmetal is covalent. Okay, so this is what iodine actually looks like, right? We can draw our Lewis structure. And it's sharing electrons. Now the question is iodine, I2, is it sharing electrons evenly or unevenly? And how would I know? How would I know if this was polar or nonpolar covalent? Electronegativity. Yeah, and you don't have to have an electronegativity chart to figure this one out, okay? What we want to do is just kind of think through it a little bit. So iodine is going to have the same electronegativity as another iodine atom, right? Both of these atoms they're the same thing. So they want electrons the same amount. Or in other words, the difference in their electronegativity values is what? Yeah, 0. There's no difference. They want those electrons the same. So what ends up happening is they're both going to share those electrons completely evenly, and you're going to get those electrons evenly distributed throughout the molecule. So this would be, remember, if they're sharing electrons evenly, that's nonpolar covalent, right? Sharing them evenly. So it's nonpolar. So let's say no, nonpolar. And then also like dissolves like. All right, what about the last one? Hydrochloric acid. Is it ionic, covalent? Okay, it's covalent, right? It's covalent. Why is it covalent? 2 nonmetals. All right, so we got 2 nonmetals bonded together. All right, so let's just go ahead just for fun. Let's draw our Lewis structure. Looks like that. So hydrogen is bonded to chlorine. And let's think about whether this is going to be polar covalent or nonpolar covalent. Do you think hydrogen and chlorine, even without looking at electronegativity chart, do you think they have the same electronegativity value? No, they don't. Chlorine's all the way on the right of the periodic table and hydrogen's all the way on the left. If electronegativity increases as you go up and right on the periodic table, they're not going to have the same electronegativity value. If you wanted to be super careful, you would want to look at the electronegativity values. And if that was ever the case, if I had a question like this on an exam, which I probably wouldn't, then I would give you an electronegativity chart. So don't think you have to memorize those. The types of questions that'll be on the exam would be some of the more clear ones. So something like this where it's definitely ionic, or something like this where it's definitely nonpolar. Okay. For something like HCl, it's a little bit more tricky, so I probably wouldn't put that one on an exam. But if I did, I would give you an electronegativity chart and you could be more certain. But let's just look at this. So if we have chlorine, which we think is probably more electronegative, and it is, and hydrogen, which is less electronegative, that hydrogen is going to have a partial positive charge and that chlorine is going to have a partial negative. So we're going to have a lot more electrons on this side of the molecule than this side. Okay, so, and that's what ends up happening. So this actually is a polar molecule. So we would say, yeah, it would dissolve in water, and it does. Right, we have hydrochloric acid solutions all the time, right? When I say 3 molar HCl, that means it was dissolved in water, and this is showing you the concentration, right? You might also see HCl with a Q next to it. Okay, so I think that's it for this video, and I hope that makes sense. If you have any questions, of course, as always, let me know, and I'll see you in the next video.